Welcome! In this video, we will tackle LeetCode problem number 145, Binary Tree Postorder Traversal. This problem focuses on traversing a binary tree in postorder fashion, which means visiting the left subtree, then the right subtree, and finally the root. We'll explore efficient approaches to solve this problem together. Let's dive in. In this problem, we are tasked with performing a postorder traversal of a binary tree. A binary tree is a hierarchical data structure where each node has at most two children, referred to as the left child and the right child. The goal is to return a list containing the values of the tree's nodes as they are visited in postorder. Postorder traversal follows a specific sequence. First, the left subtree is visited, then the right subtree, and finally the root node. The input will be the root of the binary tree, where each node is represented by an object with three attributes: val, which stores the value of the node; left, which points to the left child or is none if no left child exists, and right, which points to the right child or is none if no right child exists. The output will be a list of integers, representing the values of the nodes in postorder sequence. Let's consider an example to understand how postorder traversal works. Imagine we have a binary tree represented as root equals 1, none, 2, 3. Visually, this tree looks like this. The root node is 1, which has no left child, but it has a right child node 2. Node 2, in turn, has a left child node 3. To perform a postorder traversal, we first visit the left subtree of the root. Since there's no left child for node 1, we move to the right child, which is node 2. At node 2, we visit its left child, which is node 3. Node 3 has no children, so we add its value to the result. Returning to node 2, we add its value next, and finally, we add the root node's value. This gives us the output, 3, 2, 1. Breaking down the traversal step by step for the same example, we start at the root node, which is 1. Since it doesn't have a left child, we proceed to its right child, node 2. At node 2, we check its left child, which is node 3. Node 3 has no children, so we add its value, 3, to the result list. Returning to node 2, we add its value, 2, to the result. Finally, we add the value of the root node, 1. This results in the postorder traversal output, 3, 2, 1. Now, consider another case where the binary tree is empty, represented as root equals. Since there are no nodes to traverse, the output is simply an empty list. Let's look at one more example. Here, the binary tree consists of just a single node, with root equals 1. Visually, this tree has only the root node 1, and no left or right children. In this case, the postorder traversal is straightforward. Since there are no subtrees to visit, we add the value of the root node directly to the result. This gives us the output, 1. Now, let's go over the problem's constraints. The number of nodes in the tree can range from 0 to 10,000, and the values stored in the nodes can range from -10,000 to 10,000. These constraints mean our solution needs to handle edge cases, such as empty trees or very large trees, efficiently. To summarize the edge cases we need to consider: first, if the tree is empty, the traversal should return an empty list. Second, for a tree with only one node, the result will simply be a list containing that single node's value. Third, for unbalanced trees, whether they are skewed entirely to the left or the right, the traversal must still visit all nodes in the correct postorder sequence. Finally, when dealing with very large trees containing up to 10,000 nodes, the solution must be efficient and capable of handling the traversal within these constraints. These considerations ensure that our algorithm handles all possible scenarios correctly and performs optimally. To solve the binary tree postorder traversal problem, we need to process nodes in the order of left subtree, right subtree, and then the root node. One intuitive way to achieve this is through recursion. Postorder traversal naturally aligns with recursion since it mirrors the depth-first approach of processing subtrees first and the root last. The algorithm involves defining a helper function that recursively visits the left and right subtrees, then appends the root node's value to the result list. This method is simple and elegant, with a time complexity of O(n), since each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. However, the drawback here is that recursion can lead to stack overflow in cases of very deep trees. Another approach to tackle postorder traversal is the iterative method using two stacks. This approach simulates the recursive process by explicitly managing traversal order with stacks. The first stack is used to traverse the tree in a modified order: root node, then right subtree, followed by left subtree. The second stack is then used to reverse this order, giving us the correct postorder sequence. The algorithm begins by pushing the root node onto the first stack. As nodes are popped from the first stack, they're pushed onto the second stack, and their left and right children are added to the first stack. Once all nodes are processed, the second stack's contents provide the postorder traversal. This method has a time complexity of O(n), as each node is processed twice, and a space complexity of O(n), due to the two stacks. While this approach handles deep trees well and avoids recursion, it does require additional memory for the second stack, which is a trade-off to consider. A more space-efficient iterative approach involves using only one stack. Here, we carefully manage the traversal order and track visited nodes to emulate postorder traversal. The algorithm pushes nodes onto the stack as it traverses the left subtree. Once the leftmost node is reached, it backtracks to explore the right subtree, using a variable to track the last visited node and ensure the correct traversal order. Each node is processed once, resulting in a time complexity of O(n). The space complexity is O(h), where h is the tree's height, since the stack only holds nodes along the current path. This method avoids both recursion and the need for a second stack, making it more memory efficient. However, managing the traversal state and tracking the last visited node introduces additional complexity, which can make the implementation slightly harder to understand and prone to errors. The recursive approach is chosen as the primary strategy due to its simplicity and natural fit for the postorder traversal problem. Since the traversal inherently follows a left-right root order, recursion seamlessly mirrors this structure, resulting in concise and intuitive code. While iterative methods are also effective, they introduce additional considerations. The two-stack approach, for instance, requires extra memory and involves redundant processing of nodes. The one-stack method, though more space-efficient, is more complex to implement and debug due to the need to track traversal state explicitly. Postorder traversal fundamentally relies on processing subtrees before the root, and recursion handles this elegantly by leveraging the call stack. The choice of strategy ultimately depends on the problem constraints, such as tree depth and memory limitations. Each approach to postorder traversal has its trade-offs. The recursive approach is elegant and straightforward but risks stack overflow when dealing with very deep trees. The iterative two-stack method is robust and avoids recursion, making it a good choice for deep trees, though it consumes more memory due to the second stack. The iterative one-stack approach is the most space-efficient, but its complexity makes implementation and debugging more challenging. In most scenarios, the recursive method strikes the best balance between clarity and efficiency, making it the preferred choice. However, if the tree depth is a concern, switching to an iterative strategy would be prudent to avoid stack overflow. Ultimately, the decision should account for the specific constraints and requirements of the problem at hand. In this problem, we're tasked with performing a postorder traversal of a binary tree. Postorder traversal means we visit nodes in the order of the left subtree, then the right subtree, and finally the root node. To solve this, we'll use a recursive approach, which aligns naturally with the structure of the traversal. First, we need to fully understand the traversal order. For any given node, we recursively process its left child, then its right child, and finally the node itself. This ensures the correct order. Next, we'll define a recursive function using depth-first search, or DFS, which will take two parameters, the current node we're visiting and a result list where we'll store the traversal output. Let's break this down step by step to understand how it works in greater detail. To begin, the recursive function needs to handle the base case. If the current node is null, we simply return immediately. This prevents unnecessary operations and ensures we don't attempt to access children of a non-existent node. Once the base case is handled, we move on to traversing the left subtree. By calling the recursive function on the left child of the current node, we ensure that all left descendants are fully processed before we consider the current node. After the left subtree is complete, we shift focus to the right subtree. Similarly, we call the recursive function on the right child, ensuring all right descendants are processed. After both left and right subtrees have been traversed, we finally visit the current node by adding its value to the result list. Once the entire tree has been processed, the result list contains the postorder traversal, which we return as our final output. Postorder traversal is highly suited to a recursive approach due to its structure. Each subtree is processed independently, and the parent node is visited last, which naturally mirrors the behavior of recursion. The base case, where the node is null, is crucial for avoiding errors, as it ensures that the recursion halts appropriately when we reach the end of a branch. The order of operations is equally important. By visiting the left child first, then the right child, and only then the current node, we maintain the required left-right-root sequence. It's also important to consider edge cases. For example, if the tree is empty, we should return an empty list. A tree with only one node should return a list containing just that node's value. Even in unbalanced trees, where all nodes are skewed to the left or right, the recursive approach naturally handles these structures without any additional adjustments. The implementation of postorder traversal relies on two key data structures. First, we use a binary tree, which is typically represented using a treenode class. Each node in this class has three attributes: a value, a left child, and a right child. This structure allows us to navigate and manipulate the tree as needed during the traversal. Second, we use a result list to store the values of the nodes in postorder sequence. By passing this list by reference to our recursive function, we can update it dynamically as we traverse the tree. Now, let's look at the code implementation. We start by initializing an empty result list. Then, we define a helper function called DFS to perform the recursive traversal. Within this function, we first check if the current node is null and return immediately if that's the case. Otherwise, we recursively call DFS on the left and right children, and finally, we append the current node's value to the result list. After defining the helper function, we initiate the traversal by calling DFS on the root node of the tree. Once the recursion completes, the entire tree will have been processed, and the result list will contain the postorder traversal in the correct order. This approach is both elegant and efficient, making it a great choice for solving this problem. Let's briefly analyze the complexity of this solution. The time complexity is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once, and the operations performed at each node, such as recursive calls and appending to the list, take constant time. The space complexity is O(h), where h is the height of the tree. This accounts for the memory used by the recursion stack, which grows proportionally to the depth of the tree. In the worst case, this could be the total number of nodes in an unbalanced tree. While the recursive approach is intuitive and performs well for most binary trees, it does have limitations. For example, in extremely deep or unbalanced trees, the recursion depth could exceed the system's limit, causing a stack overflow. To address this, we can use an iterative approach with an explicit stack as an alternative. This avoids recursion and handles such cases more reliably. However, for most balanced trees, recursion remains the simpler and more elegant solution. To summarize, postorder traversal is a fundamental technique in tree traversal that is efficiently implemented using recursion. Its left-right-root order aligns naturally with the recursive depth-first search process. By understanding the traversal order, base case, and recursive flow, you can solve this problem effectively. While iterative approaches are useful for specific edge cases, recursion is often the preferred choice for its simplicity and clarity in implementation. Here, we begin by defining the treenode class, which represents a single node in the binary tree. Each node contains a value, a reference to its left child, and a reference to its right child. Next, we define the solution class and within it, the function postorder traversal. This function is designed to perform a postorder traversal on the binary tree. To start, we initialize an empty list called result, which will store the values of the nodes in the correct postorder sequence. Then, we define a helper function named traverse, which will handle the recursive traversal of the tree. Inside this helper function, the first step is to check if the current node is null. If it is, we simply return, as there is nothing further to process for a null node. Otherwise, we proceed by calling traverse on the left subtree, followed by a call to traverse on the right subtree. These recursive calls ensure that we visit the left and right children of the current node before processing the node itself. Finally, we append the value of the current node to the result list, ensuring that it is added after its children have been processed. The traversal begins by calling this helper function with the root node as its argument. The only step left is to return the result list, which now contains the values of the binary tree nodes in postorder traversal order. This approach effectively captures the postorder sequence by visiting the left subtree, then the right subtree, and finally the current node for each recursive step. The use of a recursive helper function keeps the implementation clean and easy to follow, while the result list ensures we collect the node values in the desired order. This completes the process, and the function is ready to return the final output for any given binary tree. Here, we begin by importing the necessary utilities for our implementation, specifically from the java.util package. We define a class tree node to represent the nodes of our binary tree. Each node contains an integer value, val, as well as references to its left and right child nodes. 3 constructors are provided, one for an empty node, one for a node with just a value, and another for a node with a value and links to its left and right children. Next, we create the solution class, which contains the postorder traversal method. This method takes the root of the binary tree as input and returns a list of integers representing the postorder traversal of the tree. To achieve this, we initialize an empty list called result and call a helper method, traverse, passing the root and the result list as arguments. Finally, we return the result list, which will contain the values in postorder sequence once the traversal is complete. The traverse method is a private helper function that performs the actual postorder traversal. It takes 2 parameters, the current tree node and the result list where the values will be stored. The first step in this method is a base case. If the current node is null, we simply return, as there's nothing further to process. Then, we recursively call traverse on the left subtree to explore all nodes on the left side of the current node. Similarly, we recursively call traverse on the right subtree to explore the right side. After processing both subtrees, we visit the current node by adding its value to the result list. This order of operations, left subtree, right subtree, and then the node itself, ensures that the traversal adheres to the postorder sequence. To solve the problem using a recursive approach, let's start with a simple binary tree as shown in the input. The root points to the node with value 1, and we initialize an empty list called result to store our output. We then call the helper function traverse with the root node as the argument. For node 1, the function first tries to visit the left subtree, but since the left child is none, it immediately returns. Next, it moves to the right subtree, which is node 2. For node 2, the function again recursively visits the left subtree, which leads to node 3. At node 3, both the left and right children are none, so the function adds the value of node 3 to the result list, making it 3 at this point. Returning to node 2, the function completes the traversal of its left subtree and now adds the value of node 2 to the result list, updating it to 3, 2. Back at node 1, with both its left and right subtrees processed, the value of node 1 is added to the result, resulting in 3, 2, 1. Finally, the function returns this list as the output for the postorder traversal. Now, moving to a slightly larger example, we have a full binary tree. We again start with the root, node 1, and initialize result as an empty list. The helper function traverse is called with node 1, where it first attempts to recursively visit the left subtree, which is node 2. At node 2, the function moves further into the left subtree, reaching node 4. Since node 4 has no children, its value is added to the result list, making it 4. Returning to node 2, the function now processes the right subtree, which is node 5. Similarly, node 5 has no children, so its value is added to the result, updating it to 4, 5. With both subtrees of node 2 complete, the value of node 2 is added to the result, resulting in 4, 5, 2. Back at node 1, the function now traverses the right subtree, which is node 3. Since node 3 has no children, its value is added directly to the result, making it 4, 5, 2, 3. Finally, the value of node 1 is added, and the output becomes 4, 5, 2, 3, 1. In the case of a single node tree, the input consists of just the root node with value 1. We start by initializing the result list as empty and calling the helper function with the root node. Inside the function, both the left and right subtrees are checked, but since they are none, the function immediately returns from those recursive calls. The value of the root node, 1, is then added to the result list, making it 1. This is returned as the output of the traversal. To summarize, postorder traversal always processes the left and right subtrees before visiting the root. The recursive approach ensures that we handle all nodes in this order, including edge cases like empty trees and single-node trees, efficiently. To analyze the time complexity of the recursive solution for binary tree postorder traversal, we start by considering how the nodes are visited. In a binary tree with n nodes, each node is visited exactly once. When we visit a node, 3 operations take place. We recursively traverse the left subtree, then the right subtree, and finally append the current node's value to the result list. Each of these operations takes constant time, O1, per node. Since there are n nodes in total and each node is processed exactly once, the total time complexity is proportional to the number of nodes, resulting in O(n). This holds true regardless of whether the tree is balanced, skewed, or has any other structure, as the number of nodes visited does not change. Thus, the time complexity remains O(n) in the best, average, and worst cases. The space complexity of the recursive solution is influenced by 2 main factors, the recursive call stack and the result list. First, consider the recursive call stack, which depends on the height of the binary tree. In the worst case, where the tree is skewed, the height of the tree is n, leading to O(n) recursive calls. In the best case, if the tree is perfectly balanced, the height is O log n, resulting in O log n recursive calls. Next, the result list requires space to store the values of all n nodes, which contributes O(n) to the space complexity. When we combine these factors, the total space complexity depends on the tree structure. In the worst case, for a skewed tree, it is O(n) from the call stack plus O(n) from the result list, giving O(n). In the best case, for a balanced tree, it is O log n from the call stack plus O(n) from the result list, which still simplifies to O(n). Therefore, the overall space complexity is O(n). When comparing this optimized recursive solution to other approaches, we can see its advantages clearly. A naive or brute force method might involve storing the entire tree structure in memory or performing redundant traversals, which would increase both time and space complexities. In contrast, this recursive solution ensures that each node is processed only once, maintaining optimal time complexity. Iterative solutions for postorder traversal are another alternative. These typically use an explicit stack to simulate the recursive call stack. While iterative solutions can match the time complexity of O(n), they also require O(n) space for the stack in the worst case, similar to the recursive approach. Therefore, while iterative methods may avoid the function call overhead, they do not offer a significant space advantage over the optimized recursive solution. To further solidify the time complexity analysis, we can outline the mathematical reasoning behind the O(n) result. Let T(n) represent the time complexity for processing a binary tree with n nodes. For each node, we spend O(1) time processing it, along with the time required to process its left and right subtrees. This gives us the equation T(n) equals T left underscore subtree plus T right underscore subtree plus O(1). Since the left and right subtrees together consist of all n1 remaining nodes, the equation can be rewritten as T(n) equals Tk plus T and k1 plus O(1), where k is the size of the left subtree. Summing this across all nodes leads to a total time complexity of O(n). For space complexity, the recursive call stack reaches a maximum depth equal to the tree height, which is bounded by n in the worst case. The result list, requiring space for all n nodes, also contributes O(n). Altogether, the space complexity remains O(n). Both time and space complexities are optimal for this problem, making the recursive approach highly efficient. When approaching postorder traversal, there are some common mistakes to watch out for. One frequent issue is getting the traversal order wrong. Postorder traversal specifically requires processing nodes in the sequence of left, then right, followed by the root. Mixing this up, for example by performing an inorder or preorder traversal instead, will lead to incorrect results. It's essential to ensure you're following the correct sequence, and validating your implementation with test cases can help catch these errors early. Another common mistake arises when defining the base case in recursive solutions. Forgetting to handle null nodes properly can result in null pointer exceptions or incorrect behavior, especially in edge cases such as an empty tree. Lastly, iterative solutions often involve stack mismanagement. If nodes are pushed onto the stack in the wrong order, for instance, by pushing the root before the left or right child, the traversal sequence gets disrupted. Remember, the stack operations must align with the left-right root order for postorder traversal to work correctly. Another common issue with iterative solutions arises when the output isn't reversed in the root right-left approach. This method generates nodes in the reverse order of postorder traversal, so failing to reverse the result at the end will yield incorrect outputs. It's a simple but critical step to ensure correctness. Additionally, handling edge cases inefficiently can lead to problems. For example, trees with only a single node or just one subtree can expose flaws that don't appear in more balanced trees. These scenarios should be explicitly tested to ensure your solution is robust. By accounting for these edge cases, you can avoid logical errors and make your implementation more reliable. In interviews, understanding the nuances of postorder traversal can set you apart. Recognizing patterns between different traversal types such as preorder, inorder, and postorder is crucial. Postorder traversal is particularly useful in scenarios like deleting a tree, evaluating expression trees, or resolving dependencies. Iterative solutions often test your ability to manipulate a stack correctly. Being able to trace the stack state and explain your logic will demonstrate your depth of understanding. Moreover, you should be ready to discuss the trade-offs between recursion and iteration. While recursion is usually simpler and more intuitive, it can run into stack overflow issues with deep trees. Iterative solutions, on the other hand, avoid recursion limits but tend to be more complex. Interviewers may also explore optimization opportunities, such as combining postorder traversal with other operations like summing node values or performing additional processing. To broaden your preparation, consider related problems like preorder and inorder traversals, or even breadth-first traversal as seen in level-order traversal problems. These variations will help solidify your understanding of tree traversal techniques. Postorder traversal can be implemented in a variety of ways, each with its own advantages and disadvantages. The recursive approach directly follows the definition of postorder traversal, making it clean and intuitive. However, it can lead to stack overflow for very deep trees due to the recursion depth limit. An iterative approach using two stacks avoids this issue and ensures the correct traversal order, but it requires additional space for the second stack. Alternatively, the iterative approach using a single stack is more space efficient, though it's slightly more challenging to implement since it involves reversing the output at the end. For those looking to minimize space usage entirely, the Morris traversal method uses a threaded binary tree to achieve O(1) space complexity. However, it temporarily modifies the tree structure, which can make it more complex to implement. Understanding these alternatives and their trade-offs will help you choose the most appropriate method for your specific use case. Great job! We've successfully solved the binary tree postorder traversal problem and covered both recursive and iterative approaches. Remember, postorder traversal is a fundamental concept in tree problems. If you enjoyed this, please like and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!